last invited talk of the day. And it is my absolute pleasure to introduce Alex Polozov, who's a senior researcher at Microsoft Research, who works on neural program synthesis, on synthesis from natural language, and on all cool things in the intersection of machine learning and PL. Alex, please take it away.
Thank you, Hila. Okay, connection test. Everyone can see and hear me well? Earth to Houston, great. Okay, so as Hila already mentioned, I work at Microsoft Research AI. I'm currently sitting in a wonderful place in Seattle, Washington, which surprisingly is sunny today. I work in a small group called GRAIL, for Grounded Reasoning and Interactive Learning at MSR AI, which effectively is a different name for Neuro-Symbolic Program Synthesis. And this is what I'll be talking about today. This is, I warn you, a slightly different talk than most at this workshop based on this topic. So if we were in person, I would ask everyone to hold their tomatoes or anything like that, but we are remote, so there's no danger of that. So great for me. I come initially from the programming by examples background, and this is what structures the basis for this talk. We've seen lots of different wonderful industrial applications for programming by examples and demonstrations in the recent years. It all, of course, starts with data wrangling in Flashfill and its subsequent application in the PROS framework to many different tasks. Just this morning, we saw a wonderful example of web automation from Sarah and her line of work. And more recently, we've seen programming by examples applied successfully for automatic code refactoring in Visual Studio, which is known as IntelliCode refactorings, or for automatic data visualization from a wonderful work from University of Washington folks. Now, it is true indeed that PBE is growing, and there are many places where examples are the simplest and the most natural way to specify your intent. But it's not the only one. One particular issue is examples that they have to be deliberate. You actually switch into a mode of giving examples. Not every task is natural as an example-driven specification. That said, there is a way we communicate, how we communicate every specification on Earth to other human beings, other agents, and between all of us. That's natural language in English. We probably saw the noise that OpenAI made on Twitter about a few weeks ago with their GPT-3 model, which is trained only on language alone. But that said, without any fine-tuning, just with the careful priming of the model on a given task, you are able to build non-language sophisticated program synthesis-like tools. Like, for instance, this video is showing a simply built prompt-based natural language to console command application. Of course, language is also not the only specification on Earth. And of course, if you try to use language to specify complex enough tasks, it will be as sophisticated as the program itself, which doesn't help us. But the combination of the different modalities, depending on the task, I argue, is what's going to come into the next threshold of program synthesis time. We can watch this video for a long time. It goes more and more complex territory. We are not going to do that at the moment. What I'm going to talk about in this work is partly what's been known as semantic parsing, which is the term for taking an utterance in natural language and mapping it into some formal representation. And historically in machine learning, this representation has been a lambda 4 expression in a custom tailored logic. But nowadays, semantic parsing is a key term for mapping an utterance into a program, for instance, like a SQL program here on the right. And what I'm hoping to convince you throughout this talk is that A, we are in a phase of the computer science, where we can take the methods of semantic parsing and the methods of program synthesis and let them help each other and vice versa in different applications. And this is what should be interesting if you're primarily interested in program synthesis. And if you're primarily interested in AI, as many people are, program synthesis embedded into AI and question answering tasks, let them be more systematic, learn from less data, and thus you get the best of both worlds of the symbolic methods and the modern neural methods. I am going to illustrate this on 3 different projects that we've completed over the past year. They are not immediately related to each other, but they all share this common theme of the 2 worlds coming together and helping each other, with natural language being the driving force and other modalities helping. So we're going to start with the web task completion from explanations and demonstrations. This is the recent paper at ACL 2020. The goal of this work is teaching automatic agents to complete tasks from demonstrations. This is the motivation of a subfield of interactive machine learning since decades and decades back. Say, if I want to teach automatically a computer to send me NLP-related news every day in the morning, and just this utterance alone can be interpreted in so many possible ways that there is no way it will be sufficient to describe precisely what should be accomplished. But if the computer is able to get a demonstration from us, that becomes much easier. So in this case, I can teach the agent by saying, let's type the news.com at the top of the browser and actually do that, prompting a website, pressing enter, typing NLP in the search bar, pressing enter, and then selecting the 3 most recent articles and copying and pasting them into an email website. I can do that over the scope of several minutes, and I'm hoping that this demonstration alone, unlike the original utterance, should be sufficient for the agent to generalize from it and do it all on my own. So the desiderata here is that we want to do this for many different tasks so that this is personalized for every individual. We want this to be as seamless to an individual as possible, so learn from a single demonstration. The tasks can be very brittle and dangerous. For instance, one can imagine a task of automatically paying rent every month if there is no automation for it and it requires logging in every month and clicking 5 buttons to actually send it. And if our agent requires a simulator or an exploration in order to learn how to do a task, I'm not going to do that in the first place. I don't want my computer to explore how to pay rent with typing random numbers and clicking random buttons in my bank account for obvious reasons. But I do want some kind of guarantee that whatever the agent has learned, it is definitely consistent with the demonstration that I just provided. And this is the core of program synthesis, right? So in practice, in industry, this process is known as robotic process automation, or RPA, and the promise of it is taking thousands and thousands of legacy applications and forms and processes that exist every single company on Earth, learning how to perform them by watching people do it every day, and then automating this process without changing the underlying application, just automating the button clicking and number entering. Because this is just program synthesis, effectively. So from a program synthesis view, this becomes familiar to the folks in this chat. We start from a web page. We ask the user to provide us a demonstration of what we want to do on the web page. Say in this simple example, click that blue square over there. And on the other hand, some expert wrote a domain-specific language of programs that incorporate our logic of doing things on the web page. And then the program synthesizer looks at the DSL, looks at the demonstration, and picks a program from the DSL that is consistent with the demonstration, say this one. Now, this program is supposed to implement some latent reasoning of the human, clicking a square to the right of the triangle. But all we see is the click. We don't know the reasoning. So as usual in PBD and PBE, in fact, from just a click alone, you get a set of all kinds of possible programs from the DSL that are consistent with the demonstration, but we don't know which one is the intended one. So thus, we need to generalize. And historically, the solutions to this has been ask for more examples, or learn a complex ranking function over your DSL, or hard code the ranking function heuristically as you're developing your tool. There are alternatives. So let's look at this from the semantic parsing view. What if we actually had the explanation? We knew in natural language what the user wanted to do. And if we did that, that would bring us some unintentional benefits. So here's the thing. Natural language is compositional, just like programs are. Different parts of natural language softly align with parts of the programs that we intend to map them to. And these parts compose with each other in different combinations. So in fact, if I give you a single example of an utterance and a demonstration corresponding to it and learn from it, I not only improve understanding of that utterance with the right model, I improve understanding of every constituent of the utterance, which may occur in other programs, in other utterances too. And in classic view of semantic parsing, the way we would do that is we would start from an explanation, we would map it to a program using the semantic parsing model, and then execute that program on the web page to give us that trace, and then verify that the trace is consistent with the demonstration, and if not, look for other programs. But this is wasteful. We are now doing plain old machine learning mapping from language to programs without taking into account the execution of the program that we have in the first place. And this is where program synthesis comes in. We can ensure the consistency. So here's the idea. Let's flip this model around. We are going to build a generative model of natural language explanations. So in our assumption, we start from a context which gives rise to a program. And from that program, the generative model produces both the trace that we observe and the explanation that we can observe at training time. And we want, in that inference process, the inverse of generation process that is consistent with the demonstration and relevant to the explanation. Mathematically, that means that I would like to ensure that the likelihood of an explanation, given my observed demonstration, decomposes into the likelihood of a given program being consistent with the demonstration I see, and the likelihood of the explanation actually explaining that program. And that marginalizes over all programs in our DSL. Marginalization is, of course, impossible to compute. You can't enumerate all possible programs in the DSL and just test these two probabilities. But we don't need to enumerate them. That's where program synthesis comes in. So the standard technique in programming by demonstration and examples is version space algebras. I'm not going to give you a general overview of version space algebras. They were mentioned already a couple of times today already. But the point is that we have a data structure that is a concise set representation in the graph of consistent programs in the DSL. And the semantics of it is every node in that graph consistently represents all the latent subprograms that evaluate to a given value on a given input. Now, the set of choices in the VSA, after it's learned, corresponds to a specific program. And that set of choices is what we are going to call the set of latent variables denoting a program. So the action to perform, the web element of which it acts, the attributes of that web element that are relevant for action, and so on. We know how to learn this data structure using this standard programming by examples technique, i.e. inverse semantics, like in Flash Fill and Prose. And we define our generative model over these latent variables, over the VSAs, not over the programs themselves, which now gives us a way to model alignment between words in the language and these latent VSA variables, which we are going to see in a couple of slides how that actually looks like. I'm not going to delve into the training details, but effectively, now that you operationalize everything as this inference generation loop, you can train it from just a handful of examples. I think our data set is about 100 explanations and demonstrations, not more. And simply choose the best sequence of actions at test time. To test this, we employ an old environment, well, many Waldorf bits, which have built a bunch of these tasks from deleting emails, to searching, to booking flights, to selecting colors, and so forth. And in many Waldorf bits, you're expected to perform the task until the environment tells you you've done it and gives you a reward. And you're expected to generalize to new task descriptions or new web pages for the same task description. Thus, now we know how to encode many Waldorf bits of programming administration and natural language. So conditioned on a task, we want to generate a program in the DSL that performs that task. And at training time, what happens is that you get a demonstration, you synthesize a VSA of programs consistent with the demonstration, and then you optimize in tandem the generative model and the inference model that ensures that the explanation also provided at training time aligns with that program. So here's what you get. First of all, this strictly outperforms plain semantic parsing. It strictly outperforms plain program synthesis. It's not shown here on the slide, but it would be abysmal because every demonstration gives you hundreds and hundreds of consistent programs. And it is even competitive with reinforcement learning-based approaches, which actually require exploration of the environment, and we don't. We simply get a demonstration and explanation and infer immediately. Most interestingly is this. So what you learned here is language alignment, alignment between utterances and parts of your DSL and the VSA. And this is your implicit ranking function that you usually have to laboriously define over your DSL. That arises implicitly just from the explanations because of the compositionality property, because different parts of the language align well to different parts of the program. Okay, so this concludes the first part of the talk. Now I'm going to move on to a different project. And initially, it's not going to seem very aligned with the first one, but it will change. Just stay with me for 5 to 10 minutes. Okay. So this project is on database question answering. The goal of this vision is being able to automatically query unseen databases in natural language, map them to SQL programs, and execute these SQL programs to give results. In this case, we see a toy database of some employees in shops from an unknown company. And we are asking questions about largest number of products for a given shop, managers of these shops, shops that are underperforming, so below the average, and so on. This is the screenshot of our prototype. I didn't show that here on the screenshot, but if you click the output button over there, you will see that every query is actually translated to a SQL program. And this is the one that gives rise to the results. More formally, what we want to do is have a set of databases at train time. For each of those databases, we have a bunch of questions mapped with their corresponding SQL queries. And we would like to learn from them in such a way that our parser generalizes to unseen databases with zero information provided by the DBA or by the user at testing time on the database that we have never seen before. So there are setups built in the question answering community that exactly optimize this. And the most complex one is the dataset called Spider, where you have 200 different databases, pretty complex, about 5 tables per database. And there's zero overlap between the databases in training time and testing time. The sketches of the programs might overlap. The questions never do. The Spider name is just a reference to the fact that if you have 5 tables per database, there is a bunch of foreign keys that connect them together. So the whole thing grows like a spider web around you. Now, what is the problem with training a semantic parser and asking it to apply itself on an unseen database? Well, let's look at this typical example. So here we have some database of cities, countries, languages, and other information around there. We're asking what's the average life expectancy in the countries where English is not the official language. The target query is on the right. We don't know it. We expect it to generate it. So from this, we expect our model, machine learning model, to automatically understand without ever seeing the database that, okay, life expectancy phrase there actually maps to the column life expectancy in the country table. Okay, that's easy. They at least look identical. The official maps to the column is official, which should be filtered as a Boolean. Easy enough. They look similar. The country's word maps to the name column of the country table. That one is harder. Why this and not country code, a country language, or country code in the city column? The language part should filter based on the English constant, which I suppose you know easily if you look into the database itself, or if you have some other form of background knowledge, like a BERT model or knowledge base. But if you can't look into the database, there is no way for the model to immediately understand that English exactly is the constant that it's supposed to filter on. And the model is also supposed to understand all the foreign keys, relations, and the general graphical representation of the database in order to generate the right join conditions. So this is called schema encoding or schema linking problems. Understanding of the schema, as it turns out, is the hardest task for humans. The data scientists that download a new data set from the web usually spend at least half of their time tinkering with it, running simple queries, trying to understand what is actually in these columns and how they're supposed to combine them together. No wonder this is also hard for machines as well. So I'm not going to dive deeply into the machine learning parts in this talk. I'm just going to mention at the high level that the standard way of encoding all the information that is presented to you in the recent years is what's so-called transformer model. This is also the model behind the impressive GPT-3 demos from OpenAI. This is the model behind state-of-the-art neural machine translation and many other state-of-the-art applications. The core part of the transformer model is that you take in everything in the input. And in our case, the input is your question and your database representation, such as the table names and column names. And you, layer by layer, let them attend to each other, building representations or jointly informed representations of everything. So in fact, you build a graph. You learn which of these parts of the inputs are important, so they attend to each other, there's an edge between them, and which are not. And what we are given here is a way to embed some information that we already know about this graph into the encoding process. So here we're basically saying, I have some edge features. I know something about my database, like how it's actually structured as a graph. So I don't need to learn everything from scratch. And this information I can immediately get from the database engine and from my program analysis modules at inference time when I see my unseen database. Okay, without delving about it, you can compare it also with graph neural networks if you know the literature, wherein if you're in a graph neural network, you're just taking the database schema as usual and doing some analysis on it in order to generate the program. And this is also how many state-of-the-art program synthesis from natural language techniques work when they generate database queries. But you lose connections that are not in the graph. Transformers would give you connections that are not in the graph, but they lose the parts that are actually connected. Okay. The resulting process with this model that combines together the database representations and the natural language parsing, we call RAD-SQL. RAD stands for Relation Over a Transformer, but also RADs, while many people dislike them, are pretty cute animals. And right there on the left, you have the famous monument of rats that gave their lives to the progression of science in Novosibirsk, Russia. And the underlying data set is also called Spider, as you remember, and rats and spiders are common friends, especially in Halloween times. So generally speaking, this works together perfectly. In rats specifically, we take a lot of the analysis information from the databases community and embed it, as I described before, into the encoding mechanism of the semantic parsing model. And gives you one soft encoding mechanism for any relational data that you might have. Once you have that, you can now feed it into your actual program synthesizer, which builds the program AST in depth first order step by step. And that is the one that brings in the best practices of the program synthesizer. That is, it gives you by construction valid SQL, and it follows the grammar, and it can do semantic analysis of partial programs at every intermediate step. For instance, to eliminate the parts of the from clauses that the model thinks are likely, but that are actually inconsistent with the way these columns are used later. Or to, say, eliminate programs that put in too many conditions that filter down everything to a 0. And so on. This is the current state of accuracy on the spider leaderboard. The interesting parts to highlight here for the synthesis audience is that the generalization gap of these models is much, much narrower. So usually you have some idea of your performance at development time, and then when you evaluate it on the unseen data at test time, you did drop significantly because you looked at the development data as a researcher and you designed your model to work too well on the development data without regard from generalization. But here, the gap is much smaller because the model actually is able to adapt itself to an arbitrary schema much better that it has never seen. And there's no need for any target domain knowledge. In fact, we can apply it to a database that is very topical and was dear to our heart at the time of building this project, the COVID tracking database, without any fine-tuning or target domain knowledge, and start exploring things like, what's the average amount of people in the ICU, and which states have more than that average? There are some states here that you would expect to see here, but they're actually not in the output. And this is because the data in the table is empty. And you can understand this if you look at the SQL query and see what are the results that it returns. But it would be very much black box if you simply phrased it as a question answering model. Now that you have this model, we can start adding more program synthesis goodies into the mix. Say, let's get back to our underperforming shops example. So now we can start adding multimodality into the mix, where, for instance, if after the first attempt, the generated query is wrong, I can say, that can't be right. I know that, for instance, Honka, this particular shop, is a bad one. So that should be in the output, but I don't see it in the output. And that is now an example-based specification that adds in top of the previous natural language-based specification and allows you to do multimodal synthesis in order to combine the two sources of information and evidence. You can have other kinds of evidence that add into your inference process. For instance, we can proactively disambiguate via dependency tracing on the synthesizer's part, where the system, in response to your query, asks you, do you expect to consider this one, for instance? Because implicitly, that is the row that disambiguates the two generated programs, both of which have high probability according to the model, but very different semantics. And it's easy for the user to say, no, this one is actually pretty good. I wouldn't expect the program to do that. And as a model, I don't care why the user doesn't expect to see that row. I only know that it eliminates half of my programs. So that's fine. All right. So now that concludes the second part. And I think you're hopefully starting to see the connection where you can have the core target be program synthesis driven, where you expect it to generate a procedure that generalizes to many different tasks that you've seen before, and you're using natural language as a source of bias or as a source of ranking. Or maybe your ultimate task is primarily AI-driven when you want to do question answering and you use program synthesis as a sort of constraint-driven generalization enforcement. Either one works, but because their strengths are complementary and they can be combined together. So this general principle has been emerging over the past couple of years, and it's called the Neuro-Symbolic Programming. And basically what it comes down to is to say, we have two different worlds that excel at different competencies. We can combine it together by saying, let's learn what's easy to learn, things that come from raw signal, like audio and text and images. The parts that need to be reasoned about, we can extract as a program and learn that program using program synthesis. We can fuse both of these representations appropriately, and that's where most of the innovation comes in. And if you fuse them in a way that is actually differentiable and optimizable, we can optimize that end-to-end and learn both the raw perception part as well as the synthesis/reasoning part. If you want to get into more depths about this process, Swara Chaudhary wrote an excellent blog post a couple of months ago on synthesizing neurosymbolic programs. Some of the classic examples are, for instance, a known inference of graphics program by Kevin Ellis et al. From MIT. So the combination there is you're given a sketch, and the neural part is take that sketch and extract the likely discrete strokes from that sketch. And the symbolic part is, now that you have strokes, you can synthesize programs with loops and conditionals that are consistent with these strokes. And programs are the ones that generalize, and neural models are the ones that excel at pixel level learning. Both parts can be optimized jointly. So we recently applied the same principle to visual question answering, where you're given an image and you want to ask a question about that image. And the standard state-of-the-art approach is to do joint reasoning and perception in one entangled model. And when you have that, it's very difficult to disentangle the two, and you can't combine with just reasoning or just perception. So perception, for instance, is noisy and uncertain. This picture, as it turns out, is classified as a wolf and not a husky. And if you just rely on the results of that classification as given by state-of-the-art visual models, then whatever question you ask on top of it, even if it's clearly about a husky, will be answered wrongly. Now, few state-of-the-art neural models don't often have that problem because they can take in other visual cues into account, but they don't do it systematically. So in fact, if you ask a state-of-the-art model about this picture, you can ask it, is the banana ripe enough to eat? And it will answer, yes, sure, of course. You can ask it slightly differently. Are the bananas mostly green and yellow? And it will answer green. I mean, if you actually understand the concept of bananas and ripening and what is displayed in the picture, you can't, these two answers can't be true at the same time. And there are ways to test that, which is called the systematicity and consistency testing for models, but it's very hard to enforce it if you also want the model to remain accurate. So this is what we do. Basically, jumping a little bit ahead, what program synthesis allows us to do is to define the process of reasoning separately from the process of perception. The reasoning becomes a first-order logic over scene descriptions. So the things like, is there a cat to the left of all objects or not, can be represented as a formula over the atomic predicates of the ontology of your questions. And once you have that, then answering a question becomes a pipeline process of compiling it into a program or synthesizing a program that corresponds to that question, representing that program as a logical formula over the scene, and then executing that logical formula in tandem with your visual pipeline that actually looks at the pixels of the image and extracts these probabilities of something being a burger or something being of the list of something else. So this gives you an end-to-end pipeline of both a semantic parser that gives you a program the visual oracle that converts features into probabilities, and the reasoning part, that is the logic operating over these probabilities, all working together and jointly optimized to produce the right answer. And once you have that, now you can look at any given program generated. And as a program, it will be much more consistent and systematic. It will actually give the right answers on derived or similar questions than a black box neural model, even though it occasionally has a slightly smaller accuracy. Okay, so to summarize, 3 very different projects that all together come into a single line of work. Unlike examples, in some cases, natural language is much more straightforward to solicit. We can, and in fact, that is probably the case for quite a few applications where you know what you want to do and you can express it to another human being. It is difficult to write it down in code because you don't know programming. And these are not the kind of cases for which you expect a 20-line program, because for those cases, the corresponding natural language statement would also be a 20-line paragraph. But they are the crux of automation. They are the tasks with which end users and information workers and data scientists struggle most. If you don't care about that, you can also consider that natural language, it gives you a natural bias, the compositional bias for a DSL, and allows you to learn your ranking function just from pure language annotations for your programs, rather than defining it by hand. Thus, program synthesis methods and semantic parsing methods complement. We only started exploring all the different ways in which they complement, but they already work well on many, many different applications. And more generally, neurosymbolic methods combine the strengths of the 2 fields and give us models that are differentiable and can be optimized end-to-end without any domain insight, but are also program-like and thus interpretable and systematic out of the box. I'll stop there and leave the floor open for questions. And if you're interested to learn more, these links and papers should give you a lot more interesting exploration on this topic. Thank you.
All right, so we already have a couple of questions hanging around the Slido. So I will get started on those. So first of all, thank you for this talk. It was fascinating. I dare say I might be a little more sold on this than I was before.
I convinced Hila. Okay, I accomplished the goal for my talk. This is
I wouldn't go as far as, no, I'm kidding. Okay, so Ravi is asking, do comments in existing code bases serve as good starting points for natural language explanations of code? And I actually would add on top of that, do commit messages in version control?
Commit messages are a little bit further because they are often about the reasoning behind a change, not about what the change does. So they're few steps away. But comments and docstrings, when they're available and they're well descriptive, are pretty good indicators of the behavior. And in fact, this is the information on which OpenAI fine-tuned their GPT-3 model in another demo that has been making rounds on Twitter recently. Now, of course, that comes with caveats. So this works when you have seen this kind of language before. This works when you're working on a task that is similar enough to the tasks that you've seen before, and the long tail of tasks are much more prone to omissions, subtle bugs, and the like. That said, the natural language still gives you enough bias so that your result is 80% there rather than absolutely out of the neighborhood. And that is probably the key part why we're excited about this. And from 80% to consistent and executable and logically correct, we hopefully can get by more deliberate program synthesis on top of the pure natural language-based modeling or semantic parsing.
Okay, another question about the demonstration project is asking, did you compare with the domain-specific programming by demonstration tools like Helena that Sarah showed us in the morning on their own domain?
We did not, unfortunately. That would be a cool comparison. That said, so part of the system is programming by demonstration backed by version space algebras. This is needed in order for the tool to work. This is a component of it. And it in itself is a self-contained tool. And that gives us, as I mentioned earlier, hundreds of consistent programs for any demonstration. Now, we could spend time and manually write a heuristic labeling function for those, and maybe we would have gotten 80% there. But the amount of effort to annotate 100 examples with natural language logic and learn that model out of the box was vastly easier. Testing this on Helena's benchmarks would be an interesting challenge. I think that I probably need to reach out to Sarah. That's an interesting one. Thank you.
Let's see. Another question from Ravi, who is saying, very cool talk, very cool work, thanks. Is there a role for programmers or API definitions to annotate various functions with natural language utterances that describe those functions?
Yes, I mean, in fact, they often already exist. So remember the COVID tracking example, where let me jump to it very quickly. So what you see on the right is a CSV version of their data, but what they actually provide is an API. And right next to that API, they provide a documentation page. And the documentation page is perfectly semi-structured. For every endpoint, as in for every column in here, you have a single sentence description of what that column is supposed to encode. Thus, if you start from that, you are already giving directed information about how to use a particular API. It is directed to humans, not to machines, but this is possible to exploit in a similar way. APIs in code bases are a little bit more elaborate. So the documentation there usually contains a lot of noise that you would need to learn how to filter out. But it also usually provides explicit examples that you might be able to learn how to extract explicitly and leverage.
All right, thank you. And then one last question that we have, about all we have time for too. How do you control for ambiguity in natural language? For example, the program could be wrong in subtle ways because the synthesizer misunderstood the utterance.
So that is where statistics come into play. And this is actually one of the points that are key to the demonstration project. So look, in this plot, the way it's produced is that we have explicit alignment variables, and these alignment variables tell you the contribution, according to the model, of any program component, or more specifically VSA component, to a given word. And they adapt together. You get some evidence about, let me see. Yeah, you get some evidence about text from has text, but you also get some evidence about says. Or alternatively, the word below can be found with the near operator or with the below operator. So this is the compositionality part that I talked about earlier. Now, at training time, it might happen that you start with a wrong program and you align a wrong program to an utterance. The wrong program usually will be partially correct, at least somewhat. So some parts of the alignment will be boosted and learned well. some parts of the alignment will be boosted and learned poorly on that example, but there's a data set of examples. So in combination, statistically, the utterance that aligns best with most of the components in the programs will receive will be boosted, and thus after a few iterations of training, you will arrive at the right alignment. So as long as your data set is representative enough, that is, it contains different combinations of the same programs in the DSL, you will eventually arrive at the right alignment between different constituents of these programs and different constituents of the utterance, even if on an individual example, that alignment might be poor initially. I hope that answers the question. If not, I can talk a bit more easily.
Yeah, I actually want to kind of build on that question with, I guess, one last question, because we're out of questions on the Slido. There was, you know, since you brought Twitter into it, there was a lot of buzz the other day about whether the correct, I suppose, role of this kind of work would be code completion or rather code search. Like, is do you think taking all of these things that are being learned from and detaching them from their context is something that's going to essentially help or hurt the users that are trying to use it?
I'm not sure they're necessarily exclusive. So code search is an important, well-defined and crucial application. And these techniques are already making progress in code search specifically. Milton Salamanis in MSR Cambridge is probably the person who can give hours and hours of talk about his recent research on this. Now, that said, I'm a little bit more wary about natural language-driven program synthesis in the hands of developers, as opposed to in the hands of targeted applications and end users or information workers or whatnot. In the latter case, we are talking about domains that are by construction limited, and the language that we use to operate over these domains already exists. And it is the colloquial language that users already used in order to communicate with each other about the domain area. In case of programmers, you use natural language to describe potentially complex and very subtle programs. And it is known that after a certain point, the simplest way to express a program is a program. And any explanation of it in natural language effectively becomes a pseudocode. Now, you don't have to get to that point. You can still get to that only by completion or small sections, one line at a time, for instance. It has its own challenges. So for instance, it's easy to get into a mode psychologically where you're simply accepting the system's suggestions and not thinking for yourself. And you will miss a subtle bug once it inevitably arises. But that's a different challenge on its own. It's difficult to study this right now because we are technologically not quite there. The current simple inference speed for a complex enough model in order to give these suggestions will take a couple seconds. And that's order of magnitude more than you expect from a code completion. We will get through that in a couple years, and that will be the age of software engineering studies and HCI studies on how well programmers can use these kinds of language-driven models, and what are the settings in which they shine, and what are the settings in which they are more harmful than useful.
All right, let's all thank Alex again.
Thanks, everyone.
Thank you for a fascinating talk. Let me hand it back to our illustrious chair.